a session on hardware enablers for security in industrial IoT. For this session, we have Ms. Mini TT, Principal Engineer at ABB India.
Hello everybody. Welcome to the session Hardware Enablers for Security in an Industrial IoT System. This is part of the Embedded Safety and Security Summit. Welcome to the session. And if you have any questions, please feel free to type in the chat window. We will try to attend to as many questions as possible towards the end of the session. In an industrial IoT system, today the world is moving towards digitalization. So in digitalization, or in an industrial Internet of Things, we are talking about things. So let's see what are things that we are referring to. The Internet of Things is a network of physical objects or things embedded with software, electronics, sensors, etc. And they get connected to a larger network. So this network allows objects or things to collect data and then to exchange data to a larger system. Internet of Things allow objects to be sensed and controlled remotely across existing network. So what you are seeing here is a typical industrial control system environment where you have variety of things which are enabled by QR code or mounted on a ship or could be robots, and they are all collecting information, gathering information, and then exchanging with a larger system for further control and processing. And if these are the context, within the context of ABB is, I work with an organization named ABB as part of the measurement and analytics group. So here in this context, when we say industrial measurement and the things right side, please look at the right side. There are things which are measurement instruments, which are analyzers, and they are for various purposes. Most of these, what you see, there are instruments which are measuring temperature, pressure, flow, those kind of parameters, industrial parameters. And then you see gas leak detection, mobile gas leak detection, that looks at the gases and then see whether there is leakage, which is mounted on a car or which is mounted and flying as a drone, and then it can report to a larger system for identifying what is going around. There is condition monitoring, there is dynamic QR code, and then these are all integrated into larger systems like My ABB Customer Portal, or we call as ABB Ability. That is a cloud solution, the digitalization solution for ABB. So if you look at the pyramid structure of the devices and the system, you have your devices and sensors at the lowermost level. Then you have the automation system, say things like 800XA control system, distributed control system. And then you have your enterprise solution, and then further to the cloud. So the motto that we are trying to put here is measurement made easy. That is what is belonging to the department which I belong to. That's a measurement and analytics division in ABB. So the things which we refer to here are all these measuring instruments, as well as the analyzers, and then gathering information and putting it for a larger system for remote assistance. Some occasions it is enabled by QR code, sometimes it is enabled by augmented reality, also the cloud solution. And this is how the network of industrial measurement devices look like. So I believe you have got an idea of what kind of hardware are we talking about. So we are trying to explain in this session how can we bring security into this kind of control system. So if you know, the security is a whole world of time we were talking about within the software, but security has to start from the hardware itself, from the time the first power on happens and the first instruction is get executed till all your applications and the communication. So security has to be more into a holistic view, including the hardware, the software, firmware, boot, all those kind of various areas in a software execution cycle. So in this session, what we are going to look at is how can hardware enable security? How can the hardware features enable you to realize more software-enabled software environment security, as well as while connecting and talking to various interfaces, the communication security. So how do we achieve the results of confidentiality, integrity, availability? Assisted by hardware, how can we achieve this security? That's what we are trying to look at in this session. So if you look at the communication protocol, there is a move from legacy insecure protocol to secure protocols. If you see a typical control system, which are legacy systems, you will see a lot of insecure protocols used for communication, like Modbus. Many of you might be already familiar with Modbus, I assume, or Foundation Fieldbus, Profibus, other 104, DNP3. DNP3 also has a secure version of it. So these protocols are moving towards more secure version of protocols, like say, for example, OPC-UA, IEC 104, a secure version of 104, DNP3 secure, or HTTPS, even various other protocols, which are some of them which is borrowed from the IT world into the control system world, and the control system specific protocols. So these are all moving towards security, secure protocols. So how do we bring in security into this protocols communication also? That's also something which we are going to look at in this session. Okay, since we talk about communication, the technology of communication also has evolved for the control system. The legacy protocols, which are usually used to depend on serial protocols like RS-232, RS-485, or those kind of protocols, or your HART, Profibus, those kind of physical protocols, those are all moving towards more IP-based protocols. So here you see Ethernet, you have Wi-Fi, and these days some of our devices also have NFC, that is near field communication. You can go with a mobile near to the device. The mobile has an NFC enabled. So the wireless on proximity communication, we can use that NFC. Then a lot of communication towards the internet is happening also with the 4G, 5G communication, and narrowband IoT, that is another which is catching up these days. And we have Bluetooth for another proximity communication. So all these protocols, if you look at, unlike legacy communication protocols, all these enable security. So we can do your encryption, that is your confidentiality and integrity. The authenticity can be established to who are the talking partners. All these are possible with these kind of communication technology. So this is the evolution that is happening. So security also has to go hand in hand with these protocols. In fact, these protocols and these communication technologies that we are talking about, they also have underlying security built in. So we can make use of the standard or the protocol provided security. But to start with, as I mentioned, the device themselves has to be secure, and individual devices should have security assisted by the hardware. That's what we are trying to look at in this session. So let us look at how a device from manufacturer to decommission, what life cycle stages it goes through. So first, manufacturer, say like companies like ABB, you manufacture a device and then you give it towards end to the customer for deploying in a system. That's what is the end that we are talking about, and purpose that we are talking about. So in various stages, it will go through a supply chain. Okay, maybe it may go into system integrators who will take all this, assemble into a larger system and integrate a system and then test it and make it fine and see that it is good. Then it will get provisioned into a customer's network. Provisioning is one another concept where it gets identities where you can talk in a customer's network. They get in the domain of the customer, the device is identified. Whereas in the manufacturing, it is known as an ABB device. You have an identity which is linked to the manufacturer of the device. And later on, it is in operation. All the communication security and all will come into picture. So it is continuously going on. And then you have a lot of management functions throughout the life of the device. That is a firmware upgrade. You may have to do configuration changes due to various security issues that happens in the whole world. There will be updates of say patches that may come. You may have to update the patches. So these are the kind of management activities that happen for the device. Like firmware update, you have to do it securely, the configuration update, then patch management. Those are issues that I'm talking about in the management. And then ultimately decommission. Decommission is a step where you have to get rid of all your sensitive data. You purge all your sensitive data and your credentials. So it is back into a fresh clean, so that even the remnant data is not of any use for anybody who is having intentions which are not for a constructive purpose. So that is what the life cycle of the device we are talking about. So a manufacturer produces the device, then it ultimately ends up into a decommission. There can be in between, in the management, other activities that could happen. That could be repurposed. Say maybe you want to take it out of one field and one plant, then clean up the device with every sensitive information, and you may want to repurpose it for another plant in another environment. That could also be something that happens in the management of the device. So this is what we are talking, and how do we build security into each of these spaces. So let's talk about identities. So the first of all, to bring in security, we have to authenticate the device, authenticate the entities which are communicating to each other. So that is where we come with identities. So here we all must have been familiar with the popular fairy tale story that talks about its title, Little Red Riding Hood. So the story is telling that this little girl went out to meet her grandmother, and her mother advises her while starting that do not talk to strangers. So she heard that advice, do not talk to strangers. But she went on the way she met a wolf, and the wolf asked where you are going, and she told, I'm going to meet the grandmother. But then on the way, what happened was the wolf impersonated as the grandmother, and then went into the grandmother's house ahead of her, then camouflaged as the grandmother and swallowed her. So even when the advice was given, don't talk to strangers, she was not able to make out who is a stranger, because there was no concept of how to identify who is who. So if a wolf is dressed up as a grandmother, she was not able to make out. In a security world, typically what we are talking about as a spoofing attack. That's what happened in this story. So we need to have mechanism to establish identities. So how do we establish identities? If we look at the industrial world, where the protocols and standards are being talked about, 802.1 AR, that is one standard that talks about the device identities. The device identifiers or device identities that we are talking, they are two kinds here as dictated by 802.1 AR. One is called IDEV ID and an LDEV ID. IDEV ID is an initial device identifier that is given from the manufacturer themselves, like ABB gives an identifier, and that IDEV ID is typically a public-private key pair and an associated certificate. That's what we are talking about as IDEV ID. That is provided by the manufacturer, which is also known typically or commonly as a birth certificate. And LDEV ID is something which is in the locally significant identifier, which is in the customer's network. In the domain of the customer, you get an identity. So provisioning is a step that happens. The diagram which you are seeing is provisioning in the device lifecycle. In the provisioning step, what happens is the identity that is given from the manufacturer is used for obtaining an identity in the customer's network, in the operational network. When I say customer location, I mean the operational network. So this is what we call it as a secure zero-touch provisioning. So the device is given with its own IDEV ID, and a voucher or a ticket, or different standards call it in different manner, goes along with the device, which tells that this device is having this is the serial number, this is the IDEV ID, all those kind of information goes along with the voucher. You use those two, and with a zero-touch mechanism, you can provision into the network of the domain, and then it can get a communication certificate within the customer's domain or the operational network. And once you get it, you can use that identity for your certificate renewal and your revisions. So what we are talking about as identity is public-private key pair, associated certificate. That's what we are talking. So once it is operational, then you don't need the IDEV ID any further. You disable it and keep it across the life of device, unless you are looking at a repurpose or some such kind of special cases. And this is where the hardware support comes into picture. So how can we enable all this in the hardware? So we have a root of trust. A root of trust is something which is always trusted, protected by the hardware, and it is tamper-proof. To look at, we will see some examples later in the coming slide. And key generation. We need to have a facility for generating key generation. That means we need a good entropy source and a good key generation algorithm to generate key pairs, whether it is RSA key pair or ECC key pair. We need a good key generation algorithm. That's what, and the entropy in the hardware. And storage, we need a mechanism to store the keys with integrity protected and confidentiality, and some keys could be immutable keys. Storage, typically some examples are say trusted platform module or hardware security modules. We could build in similar mechanism in the base chip itself, so that except that IP, it performs the functions using the key instead of taking out the key outside. So there is no way at all to get the private key outside. That is a way key storage, the ideal mechanism in which you can work in the HSMs. And a random number, you need a random number both for key generation, for using it as a seed, and a true random number generation. These are also mechanisms that you desire in a hardware. So when I talked about randomness, one way to achieve that is physically unclonable function. So how that work is, it can also act as a random input as well as it is bound to that hardware. So it cannot be regenerated in any other hardware. How it works is SRAM based puff is one typical mechanism that is commonly used. So here it is a fingerprint. When ICs are manufactured, due to the variations in the manufacturing processes, the initial value of the memory cells will be random. Even though it is random, it is unique. That randomness is unique. So you derive that initial stage of the SRAM values and then use that as a random source for generating keys. That's what is use that as a fingerprint for generating keys. That is a concept that is in the physically unclonable function. And secure boot. How do we enable secure boot? We need specific hardware support for doing secure boot. So here we need a root of trust that is an immutable. So what we need here is the very first code itself. You need to have a mechanism for verifying the signature of the next code, and then it also needs to have the public key that can be used for verifying the next piece of code. So the very first part is the most important, where you create a hardware root of trust. Most of the cases, like say chips like IMX or some of the TI processors or even Intel processors, you will see that there is an immutable portion which can be used for verifying the signature of the next piece. From next piece onwards, you can put a signature into it. A typical digital signature will work because they are mutable code. We can build what we want into that. So typically it is a second stage bootloader, and then your operating system, then application, all of them are signature validated further. And then how to put the public key into it? So because the device manufacturers need to put the public key, so that is provided usually by e-fuses. So one-time programmable fuses. So you use the hash of the public key into a fuse and then make it immutable. So it is one-time programmable. Once done, that's it. So this is the way usually secure boot is achieved for achieving this base root of trust, so that the very first piece is immutable and it is trusted. So hardware support for secure boot, I already mentioned that we need to have the boot ROM, and there should be mechanism for detecting failures of that, and you need e-fuses for burning the public key or the equivalent public key hash value into the hardware. And some hardware also support multiple keys, like in case a key compromise happens on one, how can we fall back into a second key? So such mechanisms are also provided. It will enable the see, these devices which we are talking about, they are all long life cycle devices. They stay for long number of years. So we need to keep it for long number of years. So we have to also consider cases where could be compromises. And memory protection, this is where we want to protect your IP. There are special ways where memory can be protected, like say read protect. You cannot read from that unless the only thing read, when I mean you cannot read it as data and get the IP out of the memory. Instead, you can only have say fetch, instruction fetch and execute. Those kind of protection is what we are talking, so that the IP also is protected, because these are sensitive IP of the device manufacturers. So if we look at some of the challenges that are coming in now in this kind of device, that in the industrial world, most of these devices are low on memory and low on compute. So there is not much of space or a playground to add more and more number of chip. Say a TPM, you can put typically a TPM into it, but then it may be interfering into your power consumption. So preferably what we would prefer is have all the security mechanism in the base CPU or the controller itself, especially for low computing, low memory, low power consumption devices. So that's what I would like the industry to look at. How can we put all the security features enabled in the base chip without having multiple chips of hardware security module separate, TPM separate, those kind of designs. And then the manufacturing infrastructure, there are also challenges, like for creating say an IIoT or certificates. Typically the CAs are somewhere hosted in an internet or a cloud, the CA providers. So how do we send a certificate signing request and get it signed? Then how can we keep this manufacturing infrastructure secure? That is another challenge that we are facing. And then power consumption, when you are battery operated, And the deployment infrastructure are not typical IT infrastructure that we can expect everything in the customers. Okay, some could be small, some could be a larger system, but they are not typical IT network. And so this is a summary of the manufacturing flow that we talked about. It is to summarize what we have already mentioned. It goes through manufacturing, supply chain, provisioning, operation, management, decommission, and that is the end of the life. And to come to a summary of the security features that we are talking, we need isolated. This is a summary of what we look for in the hardware. The key information that we are trying to ask for from the hardware to enable secure designs for industrial devices. We need isolated execution environment, a secure storage of key, secure storage of data, and random number generation, key generation capability, an eFuse array, and hardware assisted cryptography or hardware based cryptography, because they will be faster and then they also can be compliant with various certification standards or security standards. Then the firmware update, an updatable firmware, updatable software, a secure boot mechanism, a facility for attestation. We didn't cover it much in detail, but an attestation is a way to see that you have actually done a secure boot. And downgrade protection, like a previous version may have security flaws which can be exploited by a non-adversary. So only allow for firmware upgrade. Then we have network connection. How do we have this network segregation? If your device is connected to multiple networks, say one for talking to internet and one for talking to the local network, how can we get this network isolation and connection? And how do we get the root of trust? That is a immutable part. And failure recovery. If a recovery happens, how can we, like typically in secure boot, if a failure happens, you can provide another signed image and then you can get a recovery. So how do we get this kind of failure recovery? These are the summary of the security features that we expect in a hardware, so that we can enable good software designs on top of it. So that is what I had to say.